Hi there. My name is Jason Gu, and during the summer after my sophomore year of high school, I attended the Carleton Summer Science Institute, or CSSI. At CSSI, I worked in a physics group which consisted of around 10 students from all around the world, as well as Spanish visiting professor Andres Aragoneses, where I attended mini lectures as well as worked in small research groups on a project led by our professor. Here, I wanted to explore the research project that my small group completed, which was on the length changes of an accelerating object, considering Einstein's theory of special relativity. So to begin, let's run through a quick crash course of the fundamental physics topics we deal with, which is Einstein's theory of special relativity. Essentially, this theory states that both space and time are interconnected as well as variant, which allow the two to be warped and bent depending on the velocity at which objects are traveling at. Two basic equations can be seen here, which reveal how much time is dilated and the lengths are contracted when an object moves with a speed v. More importantly, Einstein proposed two main postulates to generalize this entire theory of special relativity. First, that all physical laws and phenomena operate identically in all inertial reference frames, or perspectives that move with a constant velocity. For example, if I were to throw a ball up in the air while driving uniformly in a car, I wouldn't be able to tell the difference between a car situation as if I was doing the same experiment standing on the same side of a street. And the second theory, or postulate of Einstein's theory of special relativity, states that the speed of light is constant in all reference frames. And this is the idea that we're going to work off of, as it implies that nothing, not even information, can travel faster than the speed of light. So on the slide now is a picture of the poster that our group presented at the CSSI poster presentation session. Let's take a closer look at each component of our poster and explore how the time needed for forces to travel through objects can actually allow them to change in length. So let's start with a simple diagram. Imagine that we have a car which we can simplify down to a line or stick of mass with endpoints A and B on the left and right respectively. Let's say I push on point A, pushing the car to the right. Special relativity would state that point B doesn't feel the force at the same time as point A, but rather a short time after I pushed on it. As the force travels through the car at the speed of light, the mass that this force is being applied on increases as the information of the force reaches more and more of the car. Since the left side moves before the right side, we can clearly see that this car will contract in length. So the next question is, how much? Well, let's first consider a very simplistic case, assuming that the mass the force is applied on is constant. We'll start with a simple Newton's second law, or that the force applied is equal to the product of mass and acceleration. Rearranging and implementing a kinematic formula that relates the distance traveled to the acceleration as well as time, we can substitute our acceleration from equation 2 into equation 3, giving us the position of either point A or point B when we push or pull on it. To get the length of the car, we simply subtract this position of either endpoint from the total length of our car L, arriving at our final equation down here, or equation 5. But let's see this equation in action, starting first with a car that I personally love, which is your typical Ferrari. So using a program called MATLAB, we were able to plot the length versus time of a typical Ferrari, which we researched to be around 4.5 meters long, 1,500 kilograms, with an engine force of an average of 13,000 newtons. As we can see, the length of our Ferrari essentially does not change at all, which makes sense in the real world as we don't see our cars shrinking and stretching when we hit the gas. However, let's take a look at a specially designed car that we inputted, which is 100 million meters long, 1,000 kilograms, and let's say that we push on the back with a force of 100 million newtons. As we can see, the plot here shows considerable length contraction due to our applied force. And if we were to pull instead of push on this car, we can see that this car would hypothetically be stretched a large amount as well. So that's awesome and everything, but we're forgetting about a huge assumption that we made in the front of this equation, that the mass is constant. But as we previously showed on our diagram, this assumption is just flat out incorrect. So to compensate for a changing mass situation, let's assume that the car is now a stick of mass with linear mass density lambda. Adjusting for relativistic effects in the force now correctly assuming that the mass is subjected to a change with time, we can get a differential equation that can be integrated with respect to time to solve for our velocity as well as position of our endpoints. Integrating this equation was extremely messy and was done on MATLAB with specific numerical values to simplify our task. So let's once again take a look at some plots when corrected for a changing mass situation. Taking a look at our Ferrari again, we can see that there's still really no change, which once again is completely expected. However, when we see our contraction as well as expansion plots, we can notice that the length changes happen a bit more linearly with respect to time. Regardless, it's extremely comforting and reassuring to confirm that this car, with our relativistic dimensions that we inputted, still does in fact change considerably in length when subjected to these forces, either a push or a pull. So after completing our research problem, the obvious question is, so what? Well, let's examine a couple of key takeaways from our research that we completed. First, that forces can make objects either contract or expand in length, depending on whether you push or pull on them. This occurs because each point mass on an object accelerates at a different time, a consequence of special relativity and the fact that nothing can travel faster than light itself. Finally, and a bit anticlimactically, we'll never really see these length changes in our day-to-day regular lives, although it would be really amazing to see our cars turn into full-stretch limousines when we pull on them. However, being a high school student, the most amazing part of this research was how our length change calculations compare to a topic that we've learned in a high school classroom setting, which is the Lorentz contractions. Based on the equations, we can notice that Lorentz contractions depend solely on the velocity at which an object moves at, meaning that the apparent length contraction can change with the speed. And I make an important distinction when I say apparent because it's really important to note that Lorentz contractions are not so much contractions of objects, but of space itself, a topic that we talked about previously in our special relativity crash course. For example, being a kid from a Chicago suburb, if I were to run close to the speed of light along, say, Lake Michigan, I would notice that the Sears, or now called Willis Tower, John Hancock Building, as well as the Navy Pier Ferris wheel would all appear contracted to me due to the speed that I'm running at. However, the length change calculations that we made are much different. Not only does our research reveal that objects can both contract as well as expand, depending on whether we push or pull, the length changes happening is the object's mass itself. And that's the part of our special relativity discussion that excites me the most, as it could have real impacts on the future of engineering, of high-speed cars, perhaps vehicles for space travel, or who knows what. So that just about wraps up the work that I did at CSSI. I hope you enjoyed, and thank you for listening.